before we can start cleaning and organizing our data, or even check it for bias, we need to get our data into a usable format. This is where data frames come in. You might remember we talked a little bit about data frames before. In this video, we'll learn more about what data frames are and how you can use them. Let's get started. First, let's talk about what a data frame is. A data frame is a collection of columns. It's a lot like a spreadsheet or a SQL table. Here's an example of a data frame in R. It's a lot like other tables we've worked with throughout this program. There's column names and rows and cells with data. The columns contain one variable, and the rows have a set of values that match each column. We use data frames for a lot of the same reasons as tables too. They help summarize data and put it into a format that's easy to read and use. There's some things to know about data frames before working with them. We'll learn more about data frames throughout this program, but this is a great starting point. First, columns should be named. Using empty column names can create problems with your results later on. Let's think back to our example. Each of the columns are named based on the variable they represent. There's caret, cut, color, clarity, depth. All of these columns represent data about the diamonds. Next, it's important to know that the data stored in your data frame can be many different types, like numeric, factor, or character. Often, data frames contain dates, timestamps, and logical vectors. Finally, each column should contain the same number of data items, even if some of those data items are missing. Data frames are foundational. Now, let's talk about tibbles. In the tidyverse, tibbles are like streamlined data frames. They make working with data easier, but they're a little different from standard data frames. First, tibbles never change the data types of the inputs. They won't change your strings to factors or anything else. You can make more changes to base data frames, but tibbles are easier to use. This saves time because you won't have to do as much cleaning or changing data types in tibbles. Tibbles also never change the names of your variables, and they never create row names. Finally, tibbles make printing in R easier. They won't accidentally overload your console because they're automatically set to pull up only the first 10 rows and as many columns as fit on screen. Super useful when you're working with large sets of data. Data frames and tibbles are the building blocks for analysis in R, so having set standards for how they're built and dealt with is pretty important. If we all have the same understanding of what a data frame is, we can communicate more effectively. It's like we're all speaking the same language. It's also just a lot more practical. We need to be able to do things like define columns and review code easily in R. These characteristics make it easier to share your data and reproduce your analysis. Consistent data structures like data frames make it easier to operate on an entire data set. Tidy data refers to the principles that make data structures meaningful and easy to understand. It's a way of standardizing the organization of data within R. These standards are pretty straightforward. Variables are organized into columns, observations are organized into rows, and each value must have its own cell. Now that you know a little more about data frames, let's start using them. Coming up, I'll teach you how to create data frames, add data to them, and expand them. Earlier, we learned about data frames and their key characteristics. Now, we'll actually start working with them. As a data analyst, a lot of your work will depend on data frames. If you don't create a data frame, your ability to work with your data will be limited. Think about spreadsheets. That basic structure of columns and rows carries over to R. Data frames are basically the data analyst's default way to interact with data. That's why knowing how to create and work with data frames is so important. So let's check out an example. Here we'll use R's built-in data frames. One of the great things about R and R packages is that there's a lot of interesting, easy-to-access datasets built in. These datasets let you practice some of the tools we've been learning. Let's open RStudio and get started. We'll use a preloaded dataset with information about diamonds. This dataset's part of the ggplot2 package in the tidyverse, so make sure you first load ggplot2. We'll learn how to load our own datasets later too, but diamonds is a good dataset to practice with. We can load this data now by using data open and close parentheses. You might notice that when we start to type diamonds, RStudio gives us the option to select it from its drop-down menu. That's because this dataset already exists in our library. Okay, now let's add this data frame to our data viewer. There's 10 columns and 100 rows in this data frame, but we might not want to see all of it. We can use the head function to give us just the first 6 rows. This is a nice preview of the entire dataset. Accidentally printing the full data frame to the console can be annoying and can take a long time to compute. You can avoid printing the full data frame by using functions like head to get a quick preview. We can also get the structure of the data frame using functions like structure and call names. These are just 2 functions you can use to check out your data. We'll explore other functions like glimpse later on. For example, we could use the structure function to highlight the structure of this data frame. This gives us some high-level info, like the column names and the type of data contained in those columns. But if we just want to know the column names, we can use call names instead. Here we have caret, cut, color, clarity, depth, all of the columns included in this dataset. We can also use the mutate function to make changes to our data frame. The mutate function is part of the dplyr package, which is in the tidyverse. So you'll need to load the tidyverse library before you test out mutate. Let's add a new column first. All we have to do is input mutate and then tell R we want to add a new column to the diamonds data frame. We'll first call mutate, followed by the name of the data frame we want to change. Then we'll add a column and the name of the new column we want to create. Then we want to calculate this new column. In this case, to make it easier to read the caret column, we'll multiply it by 100 to create a new column, caret_2. And when we run this, presto! Our data frame has a new column. You won't lose any columns when you create the new one. The rest of the data frame will still be the same. Data frames are usually the starting point for analyzing data in R, so it's important to understand the characteristics of data frames and how to create them. Now that we've got a little more experience with data frames, we can start doing some interesting things like clean, standardize, manipulate, and visualize data. We'll go through some common tasks that you'll perform as a data analyst, but we're just scratching the surface of what you might want to do in R. We'll start with the basics and learn how to clean up our columns. There will be a reading with a handy list you can refer to afterwards too. Let's install the Here, Skimmer, and Janitor packages now. We'll go ahead and open our console. First, we'll add the Here package. This package makes referencing files easier. To install it, we'll just write install.packages, and then, in the parentheses, we'll put here. and RStudio will install it. After we install it, we'll also need to load it using library. Next, we'll install skimr and janitor. As a quick reminder, these packages simplify data cleaning tasks. They're both really useful and do slightly different things. The skimr package makes summarizing data really easy and lets you skim through it more quickly. We'll install it now. The janitor package has functions for cleaning data. After it's done installing, we'll still need to load it. Finally, we want to make sure the dplyr package is loaded since we're going to be using some of its features. There! Now we've got all the packages we need for basic data cleaning. Now, let's load some data in. Later, when you're practicing with your own data, you can use read to grab a file. For example, if you had a CSV you wanted to load, you could write read_CSV and input the file name in the parentheses. This is where the here package comes in handy. So be sure to install and load the here package before trying to save CSV files. For now, we'll load a really fun package to practice with, the Palmer Penguin package. This is a dataset we've used before, but just as a quick reminder, the Palmer Penguin data has lots of information about 3 penguin species in the Palmer archipelago, including size measurements, clutch sizes, and blood isotope ratios. And who doesn't love penguins? First, we'll install the package. So we'll type install.packages and input Palmer penguins. And then remember to load it by using the library function. And now that we've got this data loaded into our library, we can try some cleaning functions on our columns. There's a few different functions that we can use to get summaries of our data frame: skim without charts, glimpse, head, and select. The skim without charts function gives us a pretty comprehensive summary of a dataset. Let's try it out. When we run this, we get a lot of info back. First, it gives us a summary with the name of the dataset and the number of rows and columns. It also gives us the column types and a summary of the different data types contained in the data frame. Or we could use glimpse to get a really quick idea of what's in this dataset. When we run this command, it'll show us a summary of the data. There's 344 rows and 8 columns. We have species, island, measurements for bills, which are basically beaks and flippers, the penguin's body mass in grams, the sex, and finally, the year the data was recorded. We can also use head to get a preview of the column names and the first few rows of this dataset. Having the column names summarized like this will make it easier to clean them up. We can use select to specify certain columns, or to exclude columns we don't need right now. Let's say we only need to check the species column. We can input penguins, then a pipe to indicate we'll add another command, and rselect. We'll jump back into an R script because it will be easier to see. Now we have just the species column, or maybe we want everything except the species column. We'll put -species instead of species. And now we have every column but species. The select statement is useful for pulling just a subset of variables from a large dataset. This lets you focus on specific groups of variables. There's a lot of other select functions that build on this that we'll cover later on. Now that we know our column names, we've got a better idea of what we might want to change. The rename function makes it easy to change column names. Starting with the penguins data, we'll type rename, and change the name of our island column to island_new. Now, looking at our column names, we can see the column name has changed. Or, let's say we want to change our columns so that they're spelled and formatted correctly. In spreadsheet programs, as long as our column names are meaningful, they're fine. But since we have to type the column names over and over in R, we need them to be consistent. Similar to the rename function, the rename with function can change column names to be more consistent. For example, maybe we want all of our column names to be in uppercase. We can use the rename with function to do that. This will automatically make our column names uppercase. But since variable names are usually lowercase, we'll use the to lower option to change it back. The clean names function in the janitor package will automatically make sure that the column names are unique and consistent. Let's try the clean names function on our penguins data. This ensures that there's only characters, numbers, and underscores in the names. And now you know some functions for cleaning columns in your datasets. Try practicing them on your own with the Palmer Penguins data. And once you're comfortable with these functions, we'll learn even more about data cleaning in R. We've learned how to create data frames and perform some basic cleaning functions. Now, it's time to start getting organized in R. Coming up, I'll teach you some functions that'll help you organize and filter your data. These functions look a little different in R than in other tools we've used so far. But the reason we use them is still the same. If we don't organize our data, we can't turn information into knowledge. Organizing our data and comparing different metrics from that data helps us find new insights. In other words, it makes our data useful. To help us do this, we'll use the arrange, group by, and filter functions. Let's start by sorting our data. Let's keep working with the Palmer Penguins data from earlier. In case you don't remember, refer to the link below. We'll also need to load the right packages. We can use the arrange function to choose which variable we want to sort by. For example, let's say we want to sort our penguin data by bill length. We'll type in arrange and our column name. And when we execute this command, it'll return a tibble with data sorted by bill lengths. It's currently in ascending order. If we want to sort it in descending order, we just add a minus sign before the column name. And now the longest penguin bill is first. Now it's important to remember this data is just in our console. To save this as a data frame, we'll start by naming it. Then we'll input the function we used to arrange the previous version of the penguins data. When we execute this, it'll save a new data frame, and we can use view penguins2 to add it to our data viewer. This lets you save cleaned data without losing information from the original dataset. You can also sort data by using the group by function. Group by is usually combined with other functions. For example, we might want to group by a certain column and then perform an operation on those groups. With our penguin data, we can group by island and then use the summarize function to get the mean bill length. We checked out the summarize function when we introduced piping. Basically, the summarize function lets us get high-level information about our penguin data. So let's build our group by statement first. We're not interested in NA values, so we can leave those out using the drop_NA argument. This addresses any missing values in our dataset. It's important to be careful when you're using drop_NA. It's useful when doing a group level summary statistic like this, but it'll remove rows from the data. Now, let's use summarize. We'll title the summary column mean bill length millimeters. And then we'll build the mean statement. And when we run this, we get a data frame with the 3 islands and the mean bill length of the penguins living there. We can get other summaries too. For example, if we want to know the maximum bill length, we can write a similar function and replace mean with max. And now we know that the penguin with the longest bill lived on Biscoe Island. Both group by and summarize can perform multiple tasks. For example, we could group by island and species, and then summarize to calculate both the mean and max. To do that, we can write a similar command. We'll put species and island in our group by and drop any missing values. And then we can add a summarize statement with a max and mean calculation. And when we run this, we have both groupings and the max and mean. Thanks to piping, we can combine all of these cleaning and transforming tasks into one code chunk. Finally, we can filter results using the filter function. Let's say we only want data from a daily penguins. We'll start with the dataset we're using, and then add the filter. You might notice that we're using 2 equal signs here. That's on purpose. The double equals signs means exactly equal to in R. And now we have a data frame that only contains data from a daily penguins. This lets us narrow down our analysis if we need to. Being able to clean and organize data is a key step in the data analysis process, and knowing the right tool for the job is an important skill for a data analyst. R makes wrangling data easier and gives you a lot of functionality across different stages of the data analysis process. Now that we've cleaned our data, we can get ready to transform it. Coming up, we'll learn about the separate, unite, and mutate functions, and how to use them to transform our data in R. So far, we've started cleaning and now working with data in R. Now, let's talk about how to transform data. Sometimes you need to be able to break up a variable across multiple columns, or combine existing columns, or even add new values to your data frame. Coming up, we'll use the separate, unite, and mutate functions to transform our data in R. Luckily, the packages already downloaded into our library have some tools we can use to do just that. Let's open RStudio Cloud and check them out. To start, we'll create a data frame from scratch. For this example, we'll create a standard data frame so that we can test out other functions. But you could also make a tribble here, since we're manually inputting the data. You'll learn more about tribbles in a reading. For our dataset, we're going to copy and paste some data to create our own data frame. If you want to use the same data to follow along, check out the earlier reading. Our data contains employee information, including names and job titles. You can just copy it in. We can then name the data frame employee. indicate the column names as ID, name, and job title, and print the whole data frame. Right now, the first and last names are combined into one column. We can use the separate function to split these into separate columns. We'll start with separate, and then the data frame we want to work with, and the column we'd like to separate. Then we'll add what we'd like to split the name column into. We'll just name these new columns first name and last name. And finally, we'll tell R to separate the name column at the first blank space. When we run this, it'll build us new columns for the first and last names. The separate function has a partner, unite. The unite function allows us to merge columns together. Basically, it does the opposite of separate. Let's say we're working with the version of this data frame with two name columns, and we want to combine them. We'll copy in this data as well. Our unite statement's a lot like our separate. We'll start with unite and indicate the data frame we're referring to. Then, we'll name the column we're combining first name and last name in, and then we'll say which columns we're combining. No quotation marks needed here. And finally, we can include a space that separates them. And when we run that, those two columns are combined. In addition to separating and merging columns, we can also create new variables in our data frame using the mutate function. We worked with mutate a little bit before to clean and organize our data, but mutate can also be used to add columns with calculations. Let's go back to our penguin dataset. Right now, the body mass column's measured in grams. Maybe we want to add a column with kilograms. To do that, we'll use mutate to perform the conversion and add a new column. And it'll return a tibble with our new column. You can make calculations on multiple new variables by adding a comma. Let's add a column converting the flipper length too. Now we've learned how to transform existing data in our tables and how to create new variables. Separate, unite, and mutate are some basic functions that we'll keep building on. And you might discover new ways to use them while you're practicing too. Coming up, we'll talk more about summarizing data frames and how to address bias. Earlier, we talked about summarizing data in R, and we even used the summarize function to calculate the mean for one of our penguin data variables. Now, we'll work with a very famous data example, Anscombe's quartet. Anscombe's quartet has 4 data sets that have nearly identical summary statistics, but those summary statistics might be misleading. Data visualizations, especially for data sets like these, are so important. They help us discover things in our data that would otherwise remain hidden. Plus, you'll discover some of the ways R can create awesome visualizations. Let's install the packages. This may take a few minutes to load. Okay, let's load the Anscombe's quartet data now. When we view this data, we notice that there's 4 sets of X and Y axes in the data frame. That's the quartet. Data can be summarized by different statistical measures. We'll get a summary of each set with the mean, standard deviation, and correlation for each of these data sets. We'll start by indicating that we want to group our data by set. Then we'll input our summarize function. When we run this, we'll get a summary of these statistical measures. In our summary tibble, we can check the mean. The mean for x in each dataset is 9, and the mean for y is 7.5. Standard deviation can help us understand the range of values in a dataset, and the standard deviation for x and y in every set in the quartet is the same, 3.32 and 2.03. Finally, we've got our correlation, which shows us how strong the relationship between two variables is. Here, it looks like the correlation between x and y in all four sets is around 0.816. So, based on the summaries we created with our statistical measures, these datasets are identical. But sometimes, just looking at the summarized data can be misleading. Let's put together some simple graphs to help us visualize this data and check if the datasets are actually identical. You'll learn more about plotting data in R later, but for now, we'll just get a quick idea of how this data appears. Check it out! These four datasets appear quite different when we visualize them. If we'd just gone with the statistical summaries, we never would have known that this data is actually really different. I want to show you one more really cool thing, the Datasaurus package. The Datasaurus creates plots with the Anscombe data in different shapes. But let's run it to see that for ourselves. First, you'll start off with installing and loading the package. Then, we'll create a chart. It's okay if these commands seem complicated. You'll be creating your own plots soon. This is just a sneak peek at how R can help you create data visualizations. When we run this, it shows us several different plots. There's the famous dinosaur, a bullseye, a star. R is a pretty powerful visualization tool. You could use the relationships between data points to create many other shapes. As you can see, you can do a lot of things with R. Data visualizations, like the ones we just explored, help you discover so much more about the data you're working with. It's important to explore your data in multiple ways to learn a little bit more about its story. Next, we'll learn how to use R functions to check for bias. By now, you've already learned the importance of fair, unbiased data in data analysis. In R, we can actually quantify bias by comparing the actual outcome of our data with the predicted outcome. There's a pretty complicated statistical explanation behind this, but with the bias function in R, we don't have to perform this calculation by hand. Basically, the bias function finds the average amount that the actual outcome is greater than the predicted outcome. It's included in the Sim Design package, so it's helpful to install that and practice on your own. If the model is unbiased, the outcome should be pretty close to 0. A high result means that your data might be biased, a good thing to know before you analyze it. Let's say we're working with a local weather channel to determine if their weather predictions are biased. First, we'll need to install and load a package called SimDesign. We'll use the bias function to compare forecasted temperatures with actual temperatures. For this example, we'll just take a small sample of our weather data and input them here. We'll label this the actual temp. Then we'll put in the predictions. And then the bias function. When we run this, we can find out that the result's 0.71. That's pretty high. The predictions seem biased towards lower temperatures, which means they aren't as accurate as they could be. And now that the local weather channel knows, they can find the problem in their system that's causing the biased predictions. This doesn't mean that their predictions will be perfect all the time, but they'll be more accurate overall. And that's it for now.
Congratulations on finishing this video from the Google Data Analytics Certificate. Access the full experience, including job search help, and start to earn the official certificate by clicking the icon or the link in the description. Watch the next video in the course by clicking here, and subscribe to our channel for more from upcoming Google Career certificates.